Now we have a talk by Anthony Boccaletti about Sphere Plus.
Okay, so thank you, and thanks for the opportunity to present SAXO Plus. So I will do this presentation on behalf of the team, the consortium, oops, sorry, not the right one, to which several laboratories in Europe have contributed, are contributing, in France, in Italy, in Germany, and in Switzerland. And so SAXO Plus is a technology demonstrator for PCS, which is aiming to reach higher contrast than Sphere, of course, in order to be able to study planet formation all the way from very young objects to already formed planets, giant planets. So Sphere has been instrumental in the past for detecting planets, exoplanets, obtaining spectra of this object, and also observing planet-forming disk and debris disk, even recently with WISP-2, but also WISP-1, sorry, which also is showing that there is room for more detection in the future. And yet, Sphere is not able yet, if we look at the statistical analysis in this diagram, is not able to reach a deep enough contrast to detect the bulk of the giant planet population that we see here. This is a synthetic population, all the red squares. So we have to improve the contrast in this region here. And so this is the first motivation, in fact, for SAXO Plus, which is to go deeper in contrast and closer to the star in order to overlap the limit of detection of SAXO Plus and Sphere with all the planets that have been detected by radial velocity and also with Gaia. And one of the interesting topics would be to compare the dynamical masses inferred from these indirect techniques with the luminosity, the mass inferred from the luminosity in order to be able to calibrate the mass luminosity relationship, which has quite a lot of dispersion depending on the formation mechanisms. So in order to get larger contrast at closer separation, we need to correct faster, and so SAXO Plus will have a maximum frequency of 2.7 kilohertz, which is twice the maximum frequency of SAXO. The second motivation is to be able to increase the number of detectable targets, in particular to go to observe fainter star and redder star. And we see here this histogram that shows the R-band magnitude of young star in young association. So Sphere has already a very good limiting magnitude of 13.5 or something in the R-band, which means we can observe this half part of this histogram. But even PDS-70, in fact, already takes very good seeing to be able to observe, to get this kind of image quality. And other systems, like for instance the famous HLTO, which has R equal 14 or something, are not observable at all with Sphere at the moment. And still we care about that kind of system, of course, to understand planet formation. So to increase the statistic, we need to improve the sensitivity in the infrared. So SAXO Plus will have the capacity to observe stars with J-band magnitude lower than 12. So with these requirements, we have technical goals, being to demonstrate the gain in contrast with a cascaded AO system which combine a visible Shark-Hartmann in SAXO and an infrared pyramid in SAXO Plus. We also want to compare several control algorithms on the same platform and improve the correction of NCPA at low frequencies. So SAXO Plus will be fitting in this red box here. This is the optical layout here, the mechanical layout with all the components, the mechanical system, the optical system, sorry. So we have a pickoff mirror which is taking the beam from Sphere. And in the wavefront sensor part, we have an infrared pyramid, a Silhouette 1 camera, and a chip-tip modulator. And then a Boston Micro Machine deformable mirror, 34 by 34 actuators, which is driven by the RTC, the real-time computer Cosmic. And we will have also a new apodizer that we will talk about very quickly in the next slides. So one of the very specific characteristics of a two-stage system cascaded AO system is the optimization of the loop frequencies. So this table has been obtained with a semi-analytical simulation for the first and the second stage. So we have a big table with different targets. I don't know how to use this thing. So many different brightness, from very bright star to a very red star. The reddest one in our sample has a G magnitude of almost 17, and J band 12.5. And here we have seeing and tone out, so the condition of the turbulence. So for the brightest targets, both SAXO and SAXO Plus will be able to operate at the maximum frequencies, so about 1.4 kilohertz for SAXO and 2.73 kilohertz for SAXO Plus. And as we go down to red cases, in fact, the first stage has to reduce the frequency faster than the second stage. So we go down to like 10 or 25 hertz only on SAXO, while on SAXO Plus we can still run at 300 kilohertz, 300 hertz, sorry. So this is just an illustration of a few simulation of the focal plane images with the coronagraph obtained with end-to-end simulation, with the compass simulation. Again, it shows the brightness of the star and the condition of the turbulence. And so obviously for very red target, the residual is very important with SAXO, while for SAXO Plus we improve quite a lot the performances and reduce all the residual. This is another way to plot the gain here in contrast from SAXO Plus to SAXO as a function of the J-band magnitude of the star, starting with something like 5.5 magnitude. We have quite a lot of dispersion depending on the atmospheric conditions that are supposed here, but for bright star we have a gain like an order of magnitude. Then the gain is more modest for intermediate brightness, and it rises up again up to 2 orders of magnitude, of course, because just we are missing so many photons in the visible for SAXO that it does not correct anything. So in terms of coronagraphy, we are also providing new designs of coronagraph, just because the former apodizer is in sphere is limited by its own diffraction pattern. We can see here, in fact, in blue, the contrast curve. It's a simulation of SAXO, and in green of SAXO Plus with the current apodizer. And we can see the rings from the apodizer, so it's really the diffraction pattern of the apodizer. It's still to be a limitation for SAXO, but it will be really a limitation for SAXO Plus. So with the new design, we expect a much cleaner contrast in this region at a few lambda over G, as we can see here also on these images. So one of the specificity of SAXO Plus is also the ability to run different control algorithms. So we have 5 different flavors of algorithm, each studied in 5 different teams, in France, in Germany, and in Switzerland, and we will compare the performance of this algorithm to a reference controller, which is using 2 integrators in cascade. What we observed in the simulation so far is that we have an important gain if we use this type of controller, especially in presence of vibration. This is what we see here on this plot. It's a simulation again, the contrast versus the separation, and this is without with the reference controller in red, and with the new controllers. In that case, it's the DD4AO, which allows us to gain a factor of 5 in contrast. So this is really something interesting. And also this new apodizer will allow to reduce the stroke on the DM, so we'll have more margin to correct for the turbulence, and overall it will provide a more robust correction. The first stage of the correction is the correction of the NCPA, the quasi-static speckle. So we have 2 ways, in fact, to correct for that in sphere. There's already Zelda mask, so it's a Zernike mask. We can do a phase correction, in fact, and we can reach contrast lower than 10 to the minus 5. In that case, it's 1 sigma contrast, so it's not really the detection level, but it gives an ID. And the second way, which will be implemented in SAXO Plus, is to correct for the phase and the amplitude using EFC EFC correction, as we can see here, to dig a dark hole. And in that case, we can reach contrast lower than 10 to the minus 6, so quite a net gain with respect to the first solution. And then we can combine also with coherent differential imaging to improve even better this contrast. So SAXO Plus is now in the phase of procurement. So we are starting to receive many part of the system. Sorry. Okay, well, never mind. Never mind. Okay, so the mezzanine, maybe I just do it quickly. Okay. So the optical breadboard here, what we call the mezzanine in Grenoble, the deformable mirror has been received in December at Bologna. The C-RED 1 camera has been received in Geneva, and it has been tested also in Meudon in combination with the RTC. We have a new design of the platform with the new electronic cabinets and the new design of the software. So just to finish, SAXO Plus will demonstrate key technology and strategy of observation that are relevant for PCS on a routine basis. It's a cascaded IO system in extreme IO regime, which combines a visible Charcart-Mann and an infrared pyramid. We have five, in fact, optimized control algorithms, which we will compare in real condition on sky, and we will also implement focal plane wavefront sensing. The procurement is ongoing. The most critical so far is the delivery of the optics that we wait. We are waiting for that, and it will be delivered in June or July this year. So we can test we can start the first test, the first test at Bologna with all the optic electronics and the mechanic in July this year for like 5 or 6 months. And then SAXO Plus will be shipped in Lyon in France for the final test of the AO in 2027. And so we aim to be on sky. What is it? Aim to be on sky in early 2028, and then this is the contract in the case of the PCS roadmap. We are using this instrument for testing on sky, so we will have commissioning activity for about 20 nights, and then for the next 3 years, we will have access to the telescope like 5 nights per semester to continue this testing, especially for comparing the control algorithm. And then if SAXO Plus meet the performance that we expect, then we will ask this mode to be an open mode of sphere accessible to the community for science observations. Thank you.
Hi, great talk. I was just curious, do you know how, well, multi-stage question. Do you know how long you expect it to take to dig the dark hole?
A few minutes.
Okay, cool.
5 or 10 minutes, if I'm correct. Maybe Pierre can correct me.
And then
like
once you
minutes.
have it, do you plan on just leaving the DMs as is, or do you just keep doing EFC the whole time that you're on a target?
No, I think it's, yeah, you do the correction once, yes.
Okay, cool. Thanks.
So what was the most challenging aspect of retrofitting Sphere with this upgrade?
Deal with the manufacturers, wait for the procurements to come, stupid things. Political issues.
So Bruce mentioned the gain in global time lag, going down from, I think, 2 millisecond to 1.1 millisecond. What is the equivalent for SAXO Plus? I remember for Sphere it was already less than 1 millisecond, I believe, for Sparta.
So you mean the coherence time? What we have, I think we have like something like 2 milliseconds. So it's maybe it's a bit slower, but not that much. Now this is why we want to go to 3 kilohertz. The gain between 2 and 3 kilohertz is not huge. It's really for the brightest targets.
Okay, let's thank Anthony again.